So let's study what is action potential. There is cation impulse which is reaches to the cell. As we have studied earlier, the cell is at the resting membrane potential RMP, which is about minus 90 millivolt. We have to raise the action potential from 90 millivolt to the positive side. When the ion or sodium comes, it opens the previously inactivated channel, sodium voltage gated sodium channels. This is inactivation gate. This is activation gate. When the cation comes, which causes influx of sodium from outside to inside to the cell, but it opens only for the short time, the only for the about 1 millisecond. The outside opening of the channel closes this words, and inside open this words. So about some amount of potassium influx inside and potassium efflux, some amount of potassium efflux outside. Due to the efflux of potassium, the voltage gated calcium channel opens and influx more and more calcium inside, but it also starts for the short time. It also closes as the calcium influx blocks. Potassium channel opens once again, an efflux of potassium outside takes place, which causes electronegativity inside the cell. So let's take a example on the chart or the graph. There is resting membrane potential or RMP, which is 90 millivolt. When the impulse comes or cation comes, it stimulates the resting membrane potential to minus 70 millivolt due to the positive cation of the inside positivity of the cell due to the sodium ions. Then due to the potassium efflux, it reaches to the maximum depolarization. So when the calcium channel opens, the more and more electropositivity come inside the cell, so there is negative deflection. As the one time comes when the calcium influx and potassium efflux equals, then there is a plateau phase. There is a plateau phase. Plateau phase comes with the equilibrium of the calcium influx and potassium outflux. When the calcium channel blocks and potassium efflux outside, then the resting membrane potential again going to happen, and which shows the deflection, and the cell again move towards the resting membrane potential. When the cation comes, which causes resting membrane potential moves to the minus 70 millivolt. This minus 70 millivolt potential is called threshold potential. This one is depolarization phase. This one is the plateau phase. This one is the repolarization, which causes again resting membrane potential. So till now we have studied about resting membrane potential, about action potential. So let's see how they help in the myocardial contractility. Here is the cardiac impulse or the cardiac myocyte. This is the cardiac impulse which generated from the SA node to the AV node and AV node to the cardiac myocytes. We have studied earlier that when the cardiac impulse came to the cardiac myocytes, the sodium gated voltage gated sodium channel opens, which causes influx of the sodium inside, and in return there is this is the influx of the sodium inside and the efflux of the potassium outside. Then voltage sensitive calcium channel opens inside the cell from outside. So few minutes ago we have discussed about the chart about the minus resting membrane potential minus 90 millivolt to the minus 70 millivolt, which cause the rapid depolarization, then the plateau phase, and then the repolarization phase. Depolarization, and P for plateau. We have studied that the plateau phase is because of the calcium influx. So when the calcium influx takes place inside the cells, some amount of calcium reaches to the sarcoplasmic reticulum of the cell. Let's draw. This is SR or sarcoplasmic reticulum, which causes calcium influx inside the sarcoplasmic reticulum, and the more electropositivity inside the cell, which causes release of more calcium from the stored sarcoplasmic reticulum to the extracellular space. More and more calcium releases, which acts on this is muscular tissue. So zoom it presents the actin and myosin filaments. We have studied in the earlier classes. There are two cells, actin and myosin. In between this is myosin and this is actin. So we have to highlight this. This one is actin filament, this one is myosin filament, and in between there is present troponin, which is a protein, troponin, which holds or the calcium attached to the troponin itself. When the calcium released from the cells to the sarcoplasmic reticulum, the more and more sarcoplasmic reticulum releases calcium, and when the calcium releases from the sarcoplasmic reticulum, it moves to the troponin, which causes the movement of the actin and myosin filament towards itself. Actin moves inside, myosin inside, then it causes the contractility. We have studied that how electrical activity
collaborates to the formation of contractility. The mechanism of electrical conductivity, which to collaboration of contractility to the muscle, is called electromechanical coupling.
So far, we have studied how the electrical activity inside the heart or the cardiac myocytes leads to the formation of contractility inside the heart, or we can say the depolarization, or you can call the systole. We have studied the electrophysiology of heart. Right now, the two types of cells, the specialized cells and the contractile cells, the how the resting membrane potential generates. This is the mechanism. We have discussed that there are two steps to be need to the generating resting membrane potential, action potential, and how the action potential helpful in the generation of the cardiac contractility. So far we have studied this one. Thank you.